Hello and welcome back. Let's solve the next set of 5 organic questions from the JAM 2018 question paper. So the question says, question number 6, the major product formed in the following reaction is. So you have pyrrole ring where the negative charge is there on the nitrogen, that means proton has been taken away by the base, and you have K plus 2 counter as a counter ion, and then you are reacting with in presence of chloroform and a powerful base, sodium ethoxide. So whenever you see chloroform with sodium hydroxide, sodium ethoxide, it will start thinking in the Riemann-Tiemann reaction way. So in the Riemann-Tiemann reaction, if you remember, you react chloroform and sodium hydroxide in the first step and you get dichlorocarbene. So same thing will happen here. You will get a dichlorocarbene. So CCl2 and a carbene. We will see the mechanism how it is formed. That's what will happen. So this is a famous reaction. It's the name of the reaction is CMECN Denstedt rearrangement. So here it's used for the ring expansion of pyrrole ring. So let's start with the formation of dichlorocarbene. So we are having chloroform, which proton is acidic to a certain extent because negative charges on the carbon is delocalized, not delocalized, stabilized by the minus I effect of chlorine. So first step is removal of the proton by the base and you get negative charge, and then Cl minus leaves so that it becomes neutral. Now remember, though it is neutral, but see the number of carbons, number of electrons on carbon, 1, 2, 3, 4 and 5 and 6. So only 6 electrons are there. There is a vacant sp3 hybridized orbital, and therefore it is electrophilic in nature. Electrophile, when you think about electrophile, the first thing what should come to your mind is E plus. It will attract electrons, right? Now let us look at the ring. Now ring here, nitrogen will not attack, carbon will attack. Why? Because we know carbon is not as electronegative as nitrogen. Nitrogen definitely more electronegative than carbon. So nitrogen stabilizes negative charge, carbon will not. Nitrogen is more electronegative, so its lobe will be smaller when you compare to carbon's lobe with negative charge. So carbon is definitely much more nucleophilic than nitrogen. That's why you know that carbon monoxide, cyanides, they are the most poisonous substances. They go and immediately binds nucleophilic with the hemoglobin and forms carboxyhemoglobin or cyanohemoglobin. That's why they are poison. So again here, so this nitrogen pumps its electron, this comes here and it attacks on the carbon, because we saw that dichlorocarbene is electrophilic in nature. So when it attacks the carbon, gets negative charge, and then this again attacks this carbon, nitrogen gets back the negative charge, and this goes here and this opens up, Cl minus goes away and you get 3-chloropyridine. So this is a famous reaction. So the answer is option C. You get 3-chloro, this is position 1, this is position 2, and this is position 3. We generally don't use meta for pyridine because it's not a functional group on the benzene ring, it's a pyridine, so we say 3-chloropyridine. Moving on to the next question, the question says the product X in the following reaction sequence is. So you are having this cyclopentanone, you are reacting with TiCl3 and zinc copper zinc copper alloy. So when you use this is a very famous McMurray reaction. This is reductive coupling. So two ketones, they interact with each other, oxygen is lost and alkene is formed. Basically something like this I must have drawn. Yeah, basically this is the one. So two ketones interact and oxygen O2 is lost and they form a alkene. So you can see here how it happens. It goes by a radical mechanism. They give electron, then it comes, one electron comes here. So it reacts with another molecule by radical mechanism and they form like that, and they are all attached to the tin catalyst, and then they break up and oxygen gets out as titanium oxide and you are getting the alkene. what is important is next step. The first step is a very common reaction. Next step is you are reacting with cold alkaline KMnO4. So cold alkaline KMnO4, when it reacts with alkene, it will give you diol. Whereas if it was acidic KMnO4, it would have broken it. It would have worked like ozonolysis plus oxidation if aldehyde is there. So here it will form cis diol. So you can see the mechanism. This alkene, this goes and attacks this oxygen. This comes here. I think I forgot to write this. This arrow comes here, and then this comes up here, and you get like that. Then you break it up, and you get a cis diol. The last step, you are reacting in H2SO4 acidic media. So this will undergo what is called as pinacol-pinacolone rearrangement. This is also pretty simple. One of the OH will take up the proton and get OH2 plus. So it becomes a wonderful leaving group because water leaves. So water is very stable, neutral leaving group. So what happens is this oxygen lone pair goes here. Then the ring expansion happens. The CC bond breaks up. So it's very difficult for CC bond to break. But here 2-3 things are there. On the neighboring carbon, very good leaving group is there, and therefore this badly wants to react, and this oxygen is providing ankymeric assistance. So this goes and pumps electron here, and this open up attack here, this is lost, and then this water takes away this proton and you get this product. So you are getting this answer is option number D. So this option number D is your answer. Question number 8, this is a very simple Diels-Alder reaction, but of course they are asking regioselectivity. No, not regioselectivity, it's more about stereoselectivity. So when such questions are there, you have to use what is called as Endo Rule. Endo Rule is the Diels-Alder reaction which makes it kinetically favorable. Let us first see the reaction. Reaction, what happens is, this is 4n system, this is 2n system. So it is 4 plus 2 addition, 4 plus 2 addition. So 4 is the diene, 2 is the alkene. So this alkene goes and pumps electron here, this comes here, and you are getting this product. Now I have drawn both the COOET in the endo position. Now you know endo position is more sterically hindered than exo position. Exo position is sterically not hindered. Exo position is sterically not as hindered as this endo position, because you can see here 2 carbons are there which are providing steric hindrance to this substituent, whereas in the exo position only 1 carbon is there, right? So why does it form forms thermodynamically unstable? But because it is kinetically favored reaction, because of what is called as Endo Rule, and this it is defined as described as secondary orbital effect. So what happens effectively is this alkene reacts. Now what we saw is this bond goes and attacks this, and this bond comes and attacks here. So the interaction of orbitals for the new bond formation is from this bond with this bond and this bond. But there is what is called as secondary orbital assistance, just now what we talked about. So what happens is, there is a p orbital on this carbonyl. This is the ester carbonyl group, okay. So this part and this part, this will also interact with the neighboring carbon. So you can see here this interacts with it, and this orbital also interacts with it. So because of this interaction, wherever interaction is there, wherever bonding is there, energy is released. So it makes the transition state more stable. So see here, the solid line which I have made, this is what is forming the bond, right? And these two are interactions, secondary interactions, which are making the reaction faster, making the intermediate stable, and therefore kinetically favored, and therefore this attacks here. Now if you look what happens, this H they are outside, so this H and this H they are outside, and this COT they are inside, and therefore they are occupying the endo position, okay. So this is what leads to the formation of thermodynamic less stable product. The next question, the major product Y and Z in the following reaction sequence. So we can see here the first step is reaction of aniline with a we can say alpha beta unsaturated, not ketone but ester, but very similar to ketone. So now we know nitrogen is not very electronegative, it is much less electronegative than oxygen. That means this lobe is big, so it is a soft base. Okay, and we know in alpha beta unsaturated ketone, this part, this is the hard acid. Hard acid means it accepts electron. Acid is what accepts electron, base is what gives electron, right? So here, because carbon is directly attached to oxygen, now oxygen is electronegative, so it pulls the electron towards itself. So the lobe is much smaller, the electrons are being pulled towards oxygen, so this lobe also becomes smaller, so it is becomes small, orbital smaller. So hard means hard to polarize. If it is smaller, it is difficult to pull it. Whereas here the carbon is attached to another carbon through pi bond. Now there is no electronegativity difference between carbon, so the lobe is much bigger. So it is bigger, it is easy to polarize, it is easy to distort it. So it is soft base, sorry, soft acid, and this is soft base as we talked, because this lobe is also much bigger, because it is not electronegative, so easy to polarize, so it is soft. So soft will interact with soft, and that's how the reaction happens. So let us see the first step, and then we'll go to the second step, where we are attacking it with base followed by acid. Okay, let's see. So first step is this nitrogen goes and attacks here, this comes up, this goes back, takes away this proton. The nitrogen has another electron pair, this goes and attacks another molecule of alpha beta unsaturated ester, and you are getting this kind of product. This comes here same way, it goes and takes proton, you are getting this Y, right? Next what happens? Next you are interacting with a base. So now this will undergo condensation reaction. This OET minus will take away, this is Claisen condensation basically. This OET minus will take away this proton, you get negative charge. This negative charge is delocalized with this, and so this will go and attack here, this will go and attack here, this OET leaves, and you are getting this. So after that, when you attacked with sodium hydroxide, so this COET minus will be hydrolyzed to carboxylate ion, and in presence of acid becomes COH. Now what you have to remember is, if you are having carboxylic acid alpha 2 carbonyl group, then on heating it undergoes decarboxylation, CO2 is lost. This is very important, we do all this in active methylene group, so it will work here also. So this basically what happens, this oxygen lone pair goes and attacks this proton, so then you have to show that oxygen getting positive charge, so this will come up. So both can be shown in one step. So this oxygen pi orbital comes here, attacks this proton, this comes here, and carbon dioxide is lost, this comes here, and you get a enol. Now of course after that tautomerization occurs, this comes here, this picks up proton, and you are getting the ketone. So this is the Z, answer is option B. Answer is option B. And this is the answer. Okay, moving on, the last question for this video, the correct order of carbonyl touching frequency for the following compound. So carbonyl stretching frequency basically is talking about IR spectroscopy. Okay, so in IR spectroscopy the principle is Hooke's law. It basically says stronger the bonding, more will the frequency, because more energy required to vibrate it. So it directly depends upon the K, that is bond strength, inversely proportional to reduced mass. So if mass is big, bonding will be weak, and therefore if mass is more, so that means reduced mass will be more, so frequency will be low. Okay, because bond is not strong, whereas if bonding is strong, this is also higher because bonding strong, more energy will be needed to vibrate it. Here, because if mass is more, bond is weak, so less energy needed to vibrate it. Okay, it's basically kind of spring. So the stronger the spring, more it will vibrate, more energy is needed to vibrate it. Okay. uh, so aldehyde and ketone generally they are show around 1710, 1715 kind of stuff. Okay, we can say aldehyde at 1720 and ketone at 1710. Though in IR we are never very specific about the values because it is bit broad spectrum. Okay. Now looking at the esters. Esters, what happens is, did I talk about acyl halide? Okay, I have not talked about. Ester, what happens? Oxygen is there, which pulls electron by electronegative, by minus I effect, and for some reason conjugation doesn't work much here, but it pulls electron, and because it pulls electron, it makes the bond stronger. These electrons are being pulled, so this double bond becomes shorter, and therefore the strength of the bond becomes higher, and therefore IR value increases. When you come to acyl halide, yeah, acyl halide also basically same thing happens, but it has much higher value. Ester shows around 1735. Remember, ketone shows 1710. Ester is 1735, higher value. Acyl halide is even more, around 1810. Why? Because in ester some amount of reduction is there compared to conjugation, because this lone pair comes here, this comes up, and therefore some amount of single bond character comes, and if single bond character comes, then bond is weakened, so lesser energy is needed to vibrate it. Whereas chlorine has lone pair of electron in 3p orbital, so 3p will not overlap very well with the 2p orbital of this carbon. I hope you understand, and therefore conjugation is very weak, almost insignificant. So it's the only minus I effect which is working out here, and therefore it makes this bond very strong, and therefore IR value is very high, that is 1735. And if you look at amides, see, nitrogen is much less electronegative than oxygen, so it pumps electron very efficiently. This lobe is much bigger than oxygen, so overlaps very well with this carbon, and therefore it goes away, and therefore you can see much uh, stronger single bond character comes. That means bond is weakened, and therefore little bit of energy also it will start vibrating, and therefore the energy required is much less. It is around 1680 for amide, and therefore if you look at the values, so this is acyl halide, should have highest value, then should be ester, but this will have higher than, this is aldehyde and this is amide. Amide should have lowest value, and then there should be 1. So look at the one highest, so 1 highest, then 2, but it is 3 here, so that's not the right answer. So D is the right answer, 1, 2, 4 and 3. Okay, that's it for today's video. Thank you very much.